Right, so this is the assignment, which you can find as a PDF here on the website. So it's right down there under the Espresso part. You are also going to need this Espresso grammar and text format that looks sort of like this, if it will ever open. We'll come back to that in a second. Oh, there it is. So that you're going to need later. I'll talk about it in a second. So here's the assignment. How long do you expect phase 1 to take? I expect phase 1 to take a week. So hopefully due by Monday next week. So as you can see here, we have 6 phases. The first phase is to use these tools called JFlex and JavaCup to construct a scanner and a parser for the Espresso language. We'll just take a quick look at how that works, and there's more information about that in the book as well. But we'll walk through it. Section or phase 2, we need to add some action to the files that we create for JavaCup in order to build a nice syntax tree for the parse program. Then in phase 3, we're going to add something called symbol tables. That's the stuff we're going to use to check to see if variables and other names are defined before they're used. Phase 4, which is the first big one, which is type checking. And then we have a small one, phase 5, which is modifier checking. That's all that private, public, abstract stuff. And then finally, the largest phase is the last one, where we generate intermediate assembler code, which you can run through your EVM if you have one of those, or you can assemble it to real Java class files and execute those on the Java VM. Right. So there's the academic misconduct, and speaking of, there are still a number of people, roughly 15 or so, that haven't done the quiz thing on WebEx pertaining to this. So could you please do that, or else I'm going to have to send Alex to your house to do like a census. Right, so take a look at this. Let's see if I can fit this onto. It's getting a little small, but it'll go. So I suggest that somewhere, wherever you want to do this, you create a directory called Espresso. And in there, you need this file called Espresso U. And you can get that one from me. And I will show you how to get it in a second. I'll write it down in the notes as well. And you use that script to install handouts. So every time you install a handout, you get a phase 1, phase 2, phase 3, phase 4, phase 5, and phase 6. And inside each phase, you basically have the same structure. You have an include and a lib directory, which is used for libraries, and we don't have to worry about that right away. Then we have an ant build script, and basically that just says how do we compile the entire thing. Then we have two bash shell scripts. We have Espresso C, which is the Espresso compiler script. So that's the one that will run and execute your compiler. And then we have an Espresso CR, which runs and executes mine. So when you want to test your code, you can run little test files through my compiler, and you can run test files through your compiler, and you can compare the output. There are a number of fancy programs that people have written, or scripts that people have written for you to automate all of this, and we'll look at that a little later as well. Then the next one is the id.txt file. Please fill it in. Yes, you can add your own test files, and if you do, and you have some good ones, send them to me. I'll make them public then. We'll find a place to dump them so everybody can use them in future phases. So this id.txt file is what's going to identify you. The meat and potato part of this, if I can log in here, is the source directory. And right now, it has all the directories that we're going to need, but many of them will be empty. So for example, the modifier checker, the name checker, and the type checker will basically be empty right now. They just need to be there for things to compile nicely. Now, when you want to compile your project, you simply type ant. You can clean it up by typing ant clean, and if you don't want to regenerate parsers and scanners, you can just type ant espresso. I will show you how to do all this in just a second, and it'll be on the video as well, so you can go back and take a look. You are going to use CSGFMS to submit your project, so it's important that you've signed up for that. Now, if you are working in a group of 2, then please only submit one of them, or else Alex is also going to come to your door, but he's not going to take census this time. So just one of you, both names in the id.txt file. And before you do submit something, you can use this Espresso U, which is the install script, to create a tar file to hand in. So you just say ./espresso u space tar and then space and a number depending on what phase you're handing in. And as we talked about a little earlier, no, actually, this is not the stuff we talked about earlier, but there are possible extensions that could be done. And I had somebody who did a direct studies over the summer where he did all of the optimization stuff that we'll talk about in the last 2 weeks of the class. So if anybody's interested, we can talk about that later. Right, so there we go. Now, we've already talked about this scanning stuff. We're halfway through implementing this by hand, right? So just take a look at this small program here, the public class, my class, curly bracket, int field, semicolon, void, foo, open bracket, close bracket, open curly bracket, close curly bracket, close curly bracket. If I were to chop that up into tokens, then you get exactly what I just said. So you can see this, you can see these tokens in rectangles following here. So basically, we have the scanner doing that. It reads the characters. That's when we travel around in the well, it was an NFA we looked at last time, but eventually we'll get a DFA. So when we transition between states there, that's the same as eating another character off of the input when we read the source file. And when we get to one of those accepting states, we will produce an appropriate token, and we get one of these boxed in things here, which has a lexeme, which is the text that we read off of the character stream, and some information about what kind of token it is, and so on and so forth. You probably don't want to go off and read all this stuff here. I have a feeling that web.cs might not even work anymore, but you really don't need to read those documents. Now, what we're going to do is we're going to use something called Flex. Actually, so let me just go and draw something for you here. So let's just quickly talk about Flex, which is a scanner generator. Now, should we do that in green? Here is the, actually we can do better than that. There we go. So this is the JFlex program. And if we give this guy a specification, then we will get a scanner out on the other side. And of course, if I look at that scanner as a program, then if I give that a source program, then what do I get out in the end? Well, I get a token stream. And once we've got all this set up, then we can feed that token stream into a parser that will then do the syntax analysis and tell us if our source program is correct. So this follows certain rules. So it's just a specification of our terminals and non-terminals in the grammar given certain constraints. So let me show you what they look like. So if I look at a flex file, in general, it looks like 3 bits separated by double percent signs. So there's some user code at the top and some options and declarations in the middle and some lexical rules. And it's basically just the lexical rules that we have to do. We have to do in this phase. So let's just, if I can actually figure out how to do this, fill in the lexical rules only. So we've done, oh, now we got all screwed up. See if we can find our way back. Yeah. So the user code is left empty for this project, so that's easy. The options, we have a number of, see, 1, 2, 3, 4, 5, 6, 7 different options. The first one just says, when you generate some Java that represents the scanner that gets created, then please put it into a class that's called scanner with a capital S. Because then we can tell the parser when we get to it that you can get tokens by calling a certain function or method in a class called scanner. Use a 7-bit. I don't know what the other options are. I snatched this from something that was in the example package with JFlex. Pack means create a reduced size table, so you can, I think they encode it in some smart way that makes it a little slower. The %cup means create an interface that will work with Java cup, which is our scanner, our parser generator, and then to make available line and column information. Much of this syntax and the approach goes back to the 70s, 60s, and 70s, when you probably heard about some tools called, what were they called? Yak.
Yeah.
And Lex,
Yak
and Lex and Yak, which were the official sort of C-based tools for creating C code that produce scanners and parsers. There was an open source thing later on called Bison, I think, and then there's like a million different ones now, but they all basically work the same. So we don't have to do anything about that either. Then there's a little bit of Java code, and if you look at it, you can see that we keep track of what's in the current line. We count the number of lines. Where do we put these options? Oh, they're already in there. Do we put them in the? Yeah, they're going to be in the flex file. I'll show it to you. I put it all in for you. All that nonsense that makes no sense is already there in the handout. So don't sweat that yet. I just want to go through this part first, and then I'll show you what the actual file looks like. So if we look at this here, we have the current line. So that's just the characters that have been read from the current line. The line number, so that's line count. A Boolean debug, which is just a flag that tells me whether to print out information. Then some stuff to add characters or strings to a line. So that's just to make so we can do some nice error reporting. And then probably the only thing that really matters down here is this token method, and it takes in a kind, and then it does some magic. It defines a token. It adds whatever text we read since we did this last to the line. Then it creates a new token object, and we haven't looked at the token object yet, but let me just flip back to this thing here. This token stream that we have over here on the right consists of token objects. So if we're doing this from scratch, we're going to have to find or create some sort of class that can represent all our tokens. So we have to figure out what sort of information do we need to save. We'll look at that in a second as well. It sounds a little overwhelming right now, but it really isn't all that bad once you get started. So I really suggest that You cancel all your parties on the weekend and do nothing but this. No, you should be done by the weekend, so you're good. So we create this new token, and then since we're using Java Cup, we wrap it up into a symbol, and that just means it's something that can live on the parser stack, and then we return that. And that's what the parser will get when it says to the scanner, can I have another token? Then the scanner will go and do its magic, call this token function with the appropriate kind, create a token, and if you look here, you can see that the token constructor takes in the kind, so that's, what type is this? What type is this token? The actual text, that's the lexeme, and then it takes information in about what line number it was in, and from what column to what column this particular token spans. Right. Then there's some other things in there. The third part of this this section, we have all these weird looking definitions. And for example, we have something that says flid1 equals, and then blah, 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 blah. And if you remember back to, when did you learn about regular expressions originally? 456? Maybe there's, in the automata class, or maybe in 326. If you're anything like me, then you can never remember the syntax of regular expressions when you see them written down, and you got to go look it up. But if we look at this for a little while, then it's probably not that difficult to decode. So this says that an flid1 is something that's generated by the regular expression on the right. And it's a choice between the characters, and when I say character here, I mean not value 0 and 9, but the characters 0 through 9, right? So it's the characters 0 through 9, and the plus there means at least 1. So a floating point literal has to start with 1 or more characters that are the numeric digits, and then a dot, and then 0 or more choices of digits between 0 and 9, and then something called exponent in curly brackets. And this is just a way of saying, go and expand the definition of exponent, which is given right below. So if you use curly brackets, it's just an expansion. You take that name and replace it by the definition. And the curly bracket, the question mark at the end is 0 or 1 choice, or 0 or 1 repetition. So basically, it's the choice. And this sort of makes sense, because what does a floating point literal look like? Well, some digits, a dot, some digits, and maybe an exponent. And that exponent is either a little e or capital E, a plus or a minus, optional, and then at least 1 digit. So if you look at this for a little while, you'll see that this probably makes sense. And it's nice to be able to define these regular expressions above the rules, so that you can use them later on. And I've done all of those as well, so you don't have to do that, because getting people to figure out how the correct syntax for a double floating point literal that uses mathematical notation is the stuff that gets you hurt behind the dumpster. So we're not going to do that. So here's basically what we have to do. We got to figure out, am I cutting out? I'm not doing anything. I'm just sitting here.
No, you've been loud and clear the whole time.
Now Alex says I'm loud and clear.
Well, not loud, but
Okay, cool. So who was it? So Alexis, maybe twiddle your thing. All right, good. So basically, what we have to do is just. Now the guys over here are laughing at me. They knew what I meant. Yeah, that's fine. I know you two. Anyways, so the part that we have to fill in now, as I said, I've done all the other stuff at the top. So far, I haven't told you anything you had to do. Now comes the part that you have to do, and those are those lexical rules. And the lexical rules basically are write down all the regular expressions for all the terminals in the grammar, because those are representing our tokens, and then produce some, or write down some Java action code that will create the appropriate token. And luckily, we have this this token function up here. So all this Java code is just going to be calls to this token function with the appropriate kind. So shall we take a look at how that might look? So let's just go back to here. If I can actually get a new page. Here we go. So let's just talk a little bit about a token first. So a token class. Now, what's the least information we can get away with is information about the kind and probably also the lexeme. So let's just do a very simple one here. Very simple. So something like public class token. And I want something in there which is the lexeme, so that's a string. Lexeme or text or whatever. We probably want a kind as well, so something that tells me what type of token this is. And then we probably need a constructor that takes in the various bits. And then just does what all constructors do. This dot lexeme equals, oops, and this dot, what do we call it, kind, equals kind. So something like that. Now the obvious question then is, where do I get this kind from? Well, we could provide a whole bunch of different kinds in here. So we can do something where we say, for example, public static final int. That's how you do a constant. And let's see, we need something for identifiers. There's going to be more here because we're going to give we can just give it some numbers. 0, public static final.
Move your mouse off the thing because the.
Oh.
There you go. Yeah. Just move it up. Yeah.
Did that show?
Yeah, in the video it'll show the actual.
Oh yeah.
That's recorded.
Yeah. So public static final int. We need I don't know. We probably need an integer literal, and so on and so forth. So basically, we need one for each token type here, and that's not a bad token class, and maybe it isn't super simple because the only difference between this and the other, the one that we actually use, is the line number and column number information. So this is what the scanner is going to produce. It's going to produce tokens for us using this token class. So a lexical rule. Well, it looked like something like a yeah. It's the, so we can just put in a comment here. So do that in red. This is just the actual text read from the source. So there are very few situations where you need the lexeme. So for example, if you're scanning, let's say you scan the plus, the fact that you know that the token represents the plus operator, you don't need to read the lexeme to see that plus, because the fact that you're using the token to represent a plus in itself is enough. But if you represent an identifier, then you now use the kind token.id to represent all possible identifiers. But there comes a time when you actually want to know what is that identifier, right? You're not satisfied knowing later on in your compilation quest that you had an identifier. You might want to know that that variable was called X or that function was called F, and that information is what's stored in this like CME string. So it's the actual text that was scanned from the input. So if you look at go up here, then when you look at this this stream of tokens here, then public, my class, field, and foo for sure, those might be grouped into a kind that represents a whole bunch of different values. So for example, public is or actually no, public won't, but my class, that's an identifier, field is an identifier, foo is an identifier. So at some point you need to be able to extract those names from the token, because all you'll see in the token stream really is that my class, field, and foo all will just say, hey, this is an identifier. So in order to extract the actual text scanned, we need to keep that. Does that make sense? I'll take the deafening silence as a yes. Now Alex says, can I ask why do you use static, and what's the benefit of using static variables within a class? I'm assuming it declares it only for once for every token class. Yes, that's exactly what it does. So when you have something in Java that's, well, in other languages as well, when you declare something static, it means that every instance, so every object, shares those fields. So by making a field static, you don't get them replicated in every object. They just live in the class. And since all these are never changing, I declare them final as well. Then it makes sense to declare them static because they're never going to change anyways. And so when they are initialized, static, and final, and whether they're public or private, they can be considered constants. So basically, is there a const word in C++? Yes. Yes. So it's like making a constant. Right. So here's my token class. We know that we're generating token objects. So we need a regular expression, and then we need, so this is my lexical rule that we're back to now. We need a regular expression, and then we have a set of curly brackets, and in here goes some Java code to produce a token. So basically, it's going to be something like new token something something something. And this is using token from the previous slide. So for example, if I had a plus, then I can say, I can't remember if we're supposed to say return right here. We're going to have to come back and look at that, but definitely it's going to be something like new token, and then here goes the lexeme, and I don't know what that is held in for whatever system we might be pretending to use here, but it doesn't really matter. And then here we can say token dot plus. If we had something here, regular expression for an identifier, we can do something like that. And I've actually defined the regular expression for the identifier. Now, rather than having to go and grab the lexeme and all this other stuff and type in new token every time, you can see that I've given you this token function, so we can just call that one with the kind. And you can see here that YY text is the lexeme, YY line plus 1 is the line number, YY column, and YY length is used for calculating the column. And it's sort of interesting here that the YY, why is it called Y? Well, it's called Y because it was called Y in Lex, because it got that from Lex and Yak back in the 70s, and nobody ever decided to change the name, so they're called YY for no reason, right? There are no Y's in sight except for here. And the fact that you had to turn on using it, like you had to put in these options for using lines and columns, that's a legacy thing as well, that has just lived for 50 years with nobody asking any questions. Right, so we should look at some handout, and then we'll come back and look at oh well. So by the way, here's the stuff we just talked about. Oh yeah, so here we go. Let's just look at this first. Now we could do exactly what I showed you if we were doing it all from scratch ourselves, and that would make a lot of sense. So if we were just creating a scanner, so this stuff here is great. If we were just creating a scanner, so something that would produce a token stream, and it didn't have to work with any parser. The problem we might run into is these guys down here. Turns out that they can actually be generated for us by the scanner. So let me just write that down. So we'll put an arrow here, and we'll say these are actually generated for us by CUP, which is the parser generator. Why is it done that way? Well, it makes sense because we have to identify to the parser generator what all our terminals are, and since we have a list of all the terminals, we might as well generate these numbers. So they're generated by the CUP parser generator into a file that's called sim.java. So these numbers don't actually live in the token class. Well, that's not a big deal, because all I then have to do is just say sim here instead of token. So that's all right if we can get those generated for us. And it turns out that you can see here this class called sim is, and it even says there are CUP generated classes containing symbol constants, and they are public static final int, and then a whole bunch of different entries, one for every terminal from the grammar. And they have numbers 4, 38, 78, 46, and they seem rather arbitrary. And it doesn't really matter what number they have, as long as you don't reuse any of the numbers, then that's perfectly fine. But in general, and maybe we should just make a quick note on that here, and say, note the number associated with a constant in sim.java depends on the order it has in the CUP file. So for example, in the CUP file, we have to say things like terminal plus terminal ID. So basically we list all terminals. And the first one gets number 2, I think. Because 0 is end of file and 1 is error. And these are auto-generated. So if we look at if we look at the sim file that gets generated by the parser generator, we will see a bunch of these, and if you look for the lowest number you can find, I'm pretty sure it's a 2. Now, of course, the order in here doesn't matter, and the number that something gets really doesn't matter either, as long as we're consistent when we use them. Oh, and here we can see I do have to put in the name return, or the keyword return. So if I see here, so that's another example. If I see my less than, that's not a less than, that's a greater than. If I see a greater than, then I can return a new token that I get from calling this token function with the symbol GT. Now, how do I know it's going to be called GT? Well, I don't, because we could have spelled it out greater than, but it's going to be called whatever I put here, right? So terminal GT, this will then produce something, so I can say sim.gt, and this one will give me something, so I can say sim.id, and this gives me something that I can say sim.plus with. So we could use whatever names we want. I think we should use the same names. Start with the COP file and define terminals, etc. No, I don't think you should do that. I'll come to a second. I'll come to a list in just a second. You could certainly do that, but since I think we should all stick to the same names. I mean, if some of you spell out GT to greater than and whatnot, then debugging this stuff becomes a little complicated. And I don't know how it's going to go this semester, because I'm used to people coming in here, me having to debug their code for them. I suppose if you want, I'm in the office for office hours. So if you're really stuck and you need to, if you need me to see your computer, then I suppose you could come in. I'm actually here all by yourself. Yeah. Please don't sing, Ben, because yeah, we'll leave that to Celine. Right. So let's just quickly look at here. What's next down here? There's the work list. So before we get to that, I'm going to try to do this now, and this is going to be a first, because I'm going to try to oh, I had this working a second ago. There we go. So if you log into Bobby or to Java or Sally, Cardiac, Bob, no, that's not any of those servers that you are familiar with, and you go to my directory, go to CSC 460. Remember, you don't poke around in other people's directories unless you're told. I will be wearing a mask for sure if you come and visit me. That could be perceived as being rude, but yeah, sure. So go to my directory and go into the CSC 460 directory, and if you look in there, you'll see there's a whole bunch of different stuff, but the one you're interested in is the Espresso directory. So if you go into the Espresso directory, then you have a whole bunch of stuff in there. Let's see, you have AutoGen Pi and AutoGen Plus Pi. Those are Python scripts for testing all your code. They were written by a guy called Thomas Musburger back in 2012, and they are free for you to use as you wish. I know nothing about how they work, so they're not that hard. Take a look at them, figure out how they work, and you can use those if you want. Then there's espresso.jar. That's the jar file we need for the very last phase, so we don't need to do anything with that right now. That's just it's actually a compiled version of my reference compiler. I don't know what espresso old is, but I don't think we need it. Then there's the only thing that you actually need to grab from this directory. The rest can be installed, and that's this espresso u script. So if we look at that, espresso u. Then there's a whole bunch of gunky stuff in there. But let me log into my other machine. There we go. If I can remember my password. There we go. I have a directory called espresso. Actually, doesn't matter. I'm going to make an espresso 2020. And if we go in there, that's where I want to put my little script. Now that script you can get by saying SCP and then your username. Don't use my username, because if you use my username, you have to know my password, and you don't know my. Well, I hope you don't know my password. Huh?
What?
You can guess.
Probably.
So
This is my password 123.
you think you know what it is? Okay. Well, use my password then. That's fine. So you can copy it from there. CSC 460, espresso U, like that. Oh, if I did it right, actually. There we go. So there we go. Now we have this little script here. Do a chmod 755 on it just to make sure that it's executable, and then open it up. And then here on the second line it says user equals none. You put your username on here. So for me, I'm going to put my username in there.
I'm gonna start calling it chmod now.
Chmod?
I've never called it chmod. That's cool.
Oh. I normally call it chmod as well. I don't know where that came from. Anyways, so now we have a backup here which we can delete. Be careful when you delete tilde files. Back in the day when the tilde was above the enter, and I tried to delete all my tilde files by saying rm star tilde and hit the enter before I hit the tilde, I lost all my files. Yeah, that sucked. That was the night before something was due in my architecture course back in 1992. So there's anecdotes from the previous century. Right, so now I have this espresso u thingy which I can actually run. Remember, just to say // because dot is probably not in your well, I'm from. Shut up, Ben. You're just as old. So you have you don't have dot in your path, so you probably have to say / espresso u, and you have 1, 2, 3, 4, 5 things you can do. You can ask if a phase is open, so we can say espresso u is open 1, and if you're on Java, it doesn't ask for you for all of this, but it'll say phase 1 is closed, which means that you can't actually install it yet. I have a feeling I can install it because I'm special. Let's give it a go. There we go. So now I have a phase 1 directory, and if I go into that directory, then there's all the stuff that I promised you would be there. The source directory, the id.txt, there's a little bit more than I promised you. There's also this espresso.info, but don't worry about that one. Here's the id.txt file, the one that you have to fill in if you want your project graded. So basically it's just name, student ID, and email for both of the partners. or if you work alone, just yourself. If you want to run my compiler, Espresso CR, and of course you have to give it something to. That wasn't supposed to happen. No, why did it do that? It gave me back the Perl script.
Huh.
I have to talk to Jamie about this. That wasn't supposed to happen, right? Yeah, I'm gonna have to. He's been mucking about with things on the summer without me knowing. So, yeah, that wasn't supposed to happen. Right, but before we do any more here, let me just install the tests as well. So again, you can use the Espresso U, and you can say Espresso U install tests. Oh, and then a directory, so we just install them here. Then if you look in the tests directory, you'll see there are a number of different phases. Phase 1 is the one we're working on now. There's the directory for Espresso and Espresso Plus, and in each of those you have a good test and bad test. The good test should pass, the bad test should not. So if we look at good tests, there's a whole bunch of different ones here. If we just look at a small one, so we can take bin export 1, and you'll see that it's just a tiny little program. Class main, int main, return 12. So nothing. The biggest question that's raised from this is that why is this in a file called bin export, where bin is binary and there are no binary expressions in sight? But who knows? Oversight probably. I'm going to sort out that the reference thing. I don't know why it's doing that, because what we were supposed to be able to do now is is run my reference compiler, Espresso CR, with any of these tests that we want. And it should spit out something, not just the Perl code. It should actually give you a list of tokens. That's disappointing. Oh well. Anyways, in order to compile your compiler, type ant. And if you look at the output here, it says I made some directories, then I'm creating a scanner DFA, and then I'm creating a parser, and it failed. Java returned some error 100. And it says up here, error at 131.3, Java cup symbol, compilation unit has not been declared. And of course, it won't work. So how does this non-working curl script affect us being able to work on the assignment this week? It doesn't. It just means that you can't compare to mine until I get that sorted out for a couple of days. It doesn't mean you can't work on your own. You just don't have my reference compiler right now. So not a biggie. Now let's see what we have here. Go into source. There are all those directories that we had before. If we go into scanner, which would be the perfect place to put all this scanner information stuff, we'll see that there is actually, shall we just clean this project up and clean? Because then you can see what it looks like when you get it. It has the Espresso Flex file. And if we open that, then we'll see that it basically is all the stuff that we just talked about. It's in a package called scanner. It imports some stuff. It sets all the stuff that we talked about. Here's the token function. Here are all these funny classes that I've defined. I mean, look at this comment one here at the top. Who knows what that does? No one. So that's why we're not going to write it from scratch ourselves. And then here's the part where you have to do some work. I put in your code here, all the places where you have to do some work. And I started out here with abstract, boolean, break, null, open bracket, or left paren. And then I've actually done all these weird ones down here, the numeric literals. I've done all the string literals and the character literals because this is just inhuman as well. And the comments, the white space, and the identifier. So you can see here the identifier returns a sim dot. I spelled it out, identifier, but that's the one we called .id before. So it's your job to fill in this part here at the top. Okay. Now, in order to do that, we have to find all the tokens. And we could take the grammar. Let me see if I can find the grammar real quick. It is actually at the very end of this thing here. And if you look at the grammar, I've got all the terminals in boldface. So you just have to go through here and find all the stuff that's in boldface or all caps, because those are the literal terminals. So we've got some literal terminals here. We've got some keywords. Sorry, some terminals here. We've got, there's my identifier. There's the word import, and if you look really closely, you'll see this semicolon here. This semicolon, not there, but up here. That semicolon right there after import is also a terminal. Those symbols, those single ones, can be a little bit difficult to do, but basically we want to go through the grammar and find all the terminals. So let's just write a quick work list here with the right pen. So step 1, find all terminals in the grammar. You could print that out, and then you can go through it and see if you can find them all, and then you got to figure out what they're supposed to be called. But let me show you a little bit of a quicker way of actually doing this. If I could come back to where I was here. Okay. So it turns out if you go into this AST directory, this is where all our parse3 nodes are. There's my token. So I've written the token implementation for you. And you can see here at the top, we have so we called it, I didn't call it lexeme, I called it text, but and sim, that's the kind. Then I have line, char begin, and char end. So those are those 5 things that we needed in my implementation of a token. And then I have this long array here, which goes on forever and ever. And what that array is basically just one entry per terminal. So I've actually found all the terminals for you. The only problem is you got to figure out which terminal in the grammar fits with my string description here. It's probably not so hard to figure out, and the first 2 we skip, those are those entry 0 and entry 1, the end of file and error. It's probably not hard to guess that BYTE is the keyword byte. It's probably not hard to figure out that the word class, CLASS, is the class keyword. So all the keywords up here are pretty obvious. Then comes all the literals here. They're pretty obvious as well. EQ, equal, LT, less than, GT, greater than. So you will be able to match up pretty much all of them, except for the 2 that you can never remember what are, and that's probably comp and XOR. So you end up with comp and XOR being, which is which. Should we just write down here that comp is that one, and XOR is that one. Right. So here's what we're going to do. Using the names in the token array in token sim.java. Make a list. Probably do that in a file because we're going to need this later in a file with entries that look like terminal something semicolon. And the things that go here is the name that should appear in sim.java. So basically, these are the ones that we have to agree on. And the easiest way to agree on these is just to use, the names that appear in these strings, but without the double quotes. You know, you can't see when I do air quotes here, of course, but without the double quotes on. So use the names in token.java. And these should be in the same order as in the token array. In general, the order doesn't matter in the cup file. So this goes eventually goes in the cup file. Normally the order doesn't matter, but if you go and look at the bottom here, this toString method, you can see that it returns a string that starts with the word token, and then it has an entry into this names array, and it uses sim, and sim was the kind number. The kind number came from the sim.java file. Those entries came from the Java cup file, and the order in there determined what the number they got. So that's why, because I want to print out these tokens, that the order actually matters. Is this terminal file we're making? So the terminal stuff, this stuff will be just talked about here. These guys here, they eventually go into the cup file, and we were just about to finish the flex file, so the scanner file, right? And I'll show you. No, they're in the parser directory. But this was just we needed to do this in order to know what we're looking at. We needed to make an association between names and regular expressions, right? So now step 2 here is in espresso.flex. Finish adding the rules. So if I have over here, I figured out that this guy here is LT, this one is GT, etc. Then I can just go in here and make these rules. Return token sim.lt. And I can do this because I know that that one is called LT, right? Because I know that the word LT appears in that array, and we agreed that the names I should name my terminals had to match those names from that array. And I managed to get one terminal from the grammar associated with every name in there. So we know there's a one-to-one correspondence, and we're good to go. So finish those in there, right? So that's got to be step 2. Right. So let's figure out which keyboard to use here. So we go into our scanner directory, open that file, and go down. I'm sure if I figure out how to do it, there's a page down somewhere. So there goes all the keywords. I want to do this one here. Control V. How do I go back up then? Is it Control U?
Shift page up should get you up, maybe.
What are you in Emacs?
Of course I'm in Emacs. Oh, that's a silly question. That's fine. We got it. We got it. There's actually page up and page down. There are page up and page down keys that actually work on the keyboard. So yeah, we're all good, right? So fill this in, and basically it's just from the very top to where I am right here, right? So until I've done everything below there. There's just one thing that we probably should talk about real quick, and that's the Boolean literals. VI greater than Emacs, not at all. Nano greater than us. You people know what you're talking about. You're full of poo. And I just want to write this down because we need to just talk about that last thing. We only have 10 minutes left. So, note. What are the Boolean literals? Does anybody know? What are the integer literals? 1, 2, 3, 4, 5, and so on and so forth, right? So what are the Boolean literals? Well, they are true and false. No, not 0 and 1. It's true and false. 0 and 1. You know, if you say 0 and 1, then you have to say Emacs because now you're back in the 70s before anybody thought about actually doing true and false. No, in Java it's not 0 and 1. It's true and false. So what token should true return? Well, it should return the same token as false because they're both Boolean literals. Just like 1, 2, 3, 4, 7, 42, 937 all return integer literal. So this should be a Boolean literal, and this should be a Boolean literal. I think it has to be spelled out. Let's just take a look. Gotta get the keyboard again. So if we don't remember, we can open the token file, and then we can go down and see if we can find something here that looks like Boolean literal. Ah, there, Boolean literal. All right, so all spelled out. We'll do this properly. So these are both Boolean literal. One other note, and please don't make this mistake because it's going to be a pain in the ass if you do. Strings, or actually I should say the string type is capital S. So the string name starts with a capital S, just like it does in Java. Although in Espresso, strings are atomic or primitive types. But so when you put that in, make sure you put it in with an S, capital S. So if we wanted to do that, we could say Control XK, and up somewhere here. Guess it's a keyword. Capital string. Return token. Sim.string. There we go. So that's the scanner for you. Step 3. Not in red. We might have to finish this. Might have to finish this next time, but let's see. So step 3 is we need to make a list of all non-terminals. We've already done the terminals, and we have that list that we can copy into the Java cup file. So this is for the cup file. Step 4, add list of terminals, non-terminals, and the grammar to the cup file. Now, we've looked at the scanner file, that's this guy here. And it's in the scanner directory. If I go to the parser directory, we'll see that there's a file called espresso.cup. And if I open that one up, you'll see that it kind of looks a little bit like the layout of the scanner file. There's a whole bunch of gunk at the top that says, make a package called parser, import these things, and then here's some special code. Who knows what it does? When you want to scan, in other words, when you want to get the next token, then call this next underscore token on a variable called lexer. So that just gets the next token. Now comes 3 sections. The 3 sections you have to fill in. The first one is the terminals. So it says here the order here must be that of the names array in token.java. We just talked about that. So whether you want to combine them, a number of them on the same line, that's fine, but they have to come in the right order. So this is where you put in that first list you made. Then comes all the non-terminals, and I think you should just put them in as non-terminal AST. That just says that they create something of type AST. We're not going to create anything at all, so we could have just put object, but AST will do. And they all come from the grammar. Now let me just go find the grammar for you again. Where do you find all the non-terminals? Well, you find all the non-terminals on the left-hand side. So goal, literal, type, primitive type, reference type, class or interface type. But you can also get them if you're clever with a little bit of shell scripting from what happened to the here. So open a new tab. So if you go and look at this this text representation here, if you're real clever, then you download this file, you write some script stuff that grabs all the lines with a colon and then uses if I had time, I'd show off my shell scripting skills right now. I'd do it next time. But you can certainly get it from here. Like, this is a good file to use. It's also a good file to use when it comes to putting in the grammar down here at the bottom. So once you fill this in, and do it in these sections here, the order within the various sections don't matter. All derivations start with the goal keyword, and then you can see that I put in some examples here, right? So goal, and if I just quickly flip back to this guy here and we go find goal, you can see it says goal colon compilation unit. Here it says goal colon equal compilation unit semicolon. So here we're adding A colon B or C or D. Replace colon by colon equal and end in a semicolon. So I get A colon equal B or C. Actually, let's do it this way. B, C, D. Come on. Semicolon. So this is important. Be very, very careful when you do this, because if you screw up the transcription of the rules into the cup file, then you're going to get the weirdest error messages, probably saying something bad about your scanner, and it turns out that it's not the scanner at all. So be very careful about that. So we transcribe all of those like that. There is another example. So if we look at, if we look at this one here that has the literals or the primitive types, you can see that the primitive types, sorry, the terminals that are not literals are in single quotes. They should be replaced by the name of the terminal. So single quoted terminals in the grammar become all caps terminal name. So Boolean becomes Boolean. And I think that's about it. Next step, which I think is, how far did we get? 3, 4, 5, and to compile dot / espresso C to compile test files with your newly, now it becomes meta, compiled compiler. Right, so that leaves us just with one thing to do, and I've taken a little bit more of your time than I should, but I'm going to do the following: Control XS, Control XC. Phase 1 is now open, and if you give me just one more second, I just want to show you what the output looks like. So this is the sort of output you would expect. So basically, it's the only thing that the output is. Oh, wow, that's a big ass file. Is just the toString method from token.java. So you can see here we have token short. It scanned the, so well, actually let's do the bottom one here. It says token identifier X. So it scanned the identifier X in line 6, position 10 to 10. Right, so that's what hopefully comes out of my reference compiler once I get things looked at for with Jamie. Though, give me a day. Are these scripts compile espresso expected to correctly function only on Java, Bobby, etc.? No, it should work on any Linux machine. I do this on a Mac, so but yeah, do make sure before you hand things in that it actually works. We'll pick up where we were today next time, and just maybe looking. I'm sure there's some questions as well, and I'll talk to Jamie. So with that being said, have fun, get it done. Yeah. Yeah, you should be able to download the Espresso. You remember to change your the first line 2 to have your username in it, and then you should be able to do a /espresso u install 1, and it should download phase 1 and install it perfectly for you when it's due. Hopefully on Monday. No, Tuesday. We're Tuesday today, right? Who knows where we are? Where are we? What are we? What are we doing?
What day is it?
Yes.
What year is it?
Where's my breakfast? I'd like to aim for Tuesday. This is really not a big phase, and you know. So here's the thing, right? Normally, no, you're going to need a drink after the last phase, so don't start drinking yet. I don't really care when things are due, except for phase 1 has to be due before phase 2, phase 2 has to be due before phase 3, and phase 6 has to be handed in by December 5th or something like that. And this is the easiest phase, so that's why I suggest that doing it in a week is probably a good idea. But we can certainly talk more on Thursday if everything has gone bad. So that being said, office hours tomorrow. Will be here. Do me a favor, send me an email if you intend to come to office hours, at least 5 minutes before you come, because then if I have been slacking off and not made it to my office, then I can pull over in a CVS parking lot and talk to you on my cell phone, or whatever. Yes, video uploaded soon. I'll do it right away if I can get away from you people, because I've got another one starting in 10 minutes. So we'll get it up. See you all in 2 days, or maybe some of you tomorrow. All right, take it easy.